So I'm going to be looking at how we are trying to improve our measurements and modeling of this phenomenon. Okay, so as I was saying, I don't know why this is blocking the title, but that's okay. So we're characterizing the energetics and the emissions of fires during the FIREX-AQ field campaign. The AQ there represents air quality. So let me acknowledge some of my co-authors, colleagues from NOAA, from the universities, and from NASA. We worked together. This picture, I took it myself during one of the flights here in this area. This is Louisiana. We were on the plane, I looked through the window, I saw this fire, I looked at it, and then we flew over other fires. This is a small fire compared to other fires that we overflew, but at least I'm proud of taking, that I took this picture myself, so that's why I put it here on the one page. Okay.
There's a slight delay, but as you continue to move.
Okay. All right. Okay. I just clicked. Maybe it's so maybe I can use it first.
Yeah, we can use the cursor with people.
Okay. Okay. So you're looking at this. So if you studied the the elementary theories of radiation, you'll see that Weyl displacement law shows that the peak wavelength of radiation, well, at least the Planck's law, which states that every object emits radiation, and it depends on the temperature. Then when said that the peak wavelength is inversely proportional to the temperature of the body, and the B there is a constant. So fires, vegetation fires range in temperatures from about 500 Kelvin to about 1200 Kelvin, depending on whether it's flaming or smoldering. So for that particular case, if you plug this into that equation, you will find that the range of wavelengths of the peak wavelength will be about between 2.4 to about 4.8 microns. Okay. So this is an example of an airborne image. Then you will see that the wavelengths of the different channels. In the visible, you will see the smoke. You don't see the fire. But in the infrared, you will see the fire because the smoke is transparent to these infrared channels, more or less. So, but in particular, if you look here, very close to 4 microns, if you look at the other ones, you will see also some signal from the surface and from the smoke. And here you see some temperature signal from the plant surface. But here in particular, you see mostly the temperature from the fire. So it turns out that and this is a plotting of modeling of fire temperatures with wavelength. You will see that the peak is just around 4 microns. So this is important for what we're going to be talking about. Okay, so how do we calculate emissions from the measurements from satellite where we observe the fire? Sometimes we look at the fires, we just detect the hot spots, and sometimes we measure the burned area, sometimes we measure the radiant energy. So the typical traditional way to estimate emission is this formula here, where you have an emission factor which relates the quantity of biomass consumed to the amount of emission of any constituent, and then you multiply by the amount of biomass and you get the emission. But the emission, the biomass is a function of different things that opens it up to a lot of uncertainty. And those properties are the area burned, the biomass density, the biomass proportion, and so on and so forth. And this method has been used to derive some of the emission products that I use globally. For instance, in this case, the area burned was estimated from measurements from a lot of satellites, including MODIS, the older VIREX, the ATSR, and many other satellite sensors. Now, we reason that when you look at this picture, for instance, of a fire, one thing you'll notice is that there are two things that you see. The thing is the flame, that is the energy, which kind of signifies the energy, and the smoke also. And when it is flaming, you will see that it is darker, blacker smoke. So the combustion is more efficient. So what comes out is mostly black carbon. And in the other smaller areas, the smoke is whiter. So it's mostly organic material. So based on that, we are able to measure what we call the fire radiative power, which is the rate of the release of the radiative energy. And this was derived from MODIS, which you heard the last speaker talk about. And also, of course, we derived it from FIREX, which is the younger brother of MODIS. And so we were able to measure this. So we determined that the emissions, we can use this quantity we're able to characterize from satellites to derive emissions rather than looking at the burn area after the fact. So in near real time, we can measure this and then we can, so how do we do it? So then this, we have two different approaches. The first approach is that we already have the emission factor determined from lab measurements. So we just use this and convert it to the burn biomass, and we use the emission factor. The other approach is to use this directly and then derive the emission coefficient, which relates the emission of the different constituents from smoke, and just multiply by the fire radiative power to get the rate of emission, or integrate that over time, and that becomes the fire radiative energy. And so we multiply by the emission coefficient, and then we're able to get the total emissions. So these two methods have led to the development of two global emissions, fire emissions products, okay, which we're going to be looking at comparing them. So how do we derive the emission coefficient? So we developed this a few years ago, where from satellite observations of the fire radiative power and the aerosols, we're able to determine the rate of the plume using some model information about wind and other properties. And so we have this fire radiative power, which is the rate of release of the energy. And then we plot this, which is the rate of the emission of the aerosols. And we're able to find a very good relation between them. And we remove the outliers. And based on that, we're able to determine this map of graded emission coefficients globally, which we have. And so based on that, we can multiply this whenever we measure the fire radiative power, or integrate it over time, over a day, over a month, and so on. And so we're able to very easily calculate the total emissions over time. I hope that I'm getting the message across. So anyway, this, by the way, we published, this is, everything I showed here has been published already. That's not everything. Some of the things I'm showing now are this introductory part of the talk. So now, there are many different emissions products, fire emissions products that exist. So these are some of them here. Many people who do modeling that include fire emissions use some of these. GFED, two versions, FIN, GFAST, which I mentioned before, FIR, which we developed, QFED, which was also developed at NASA. Look at the globe. So the globe, we kind of regionalize the globe into fire regions. And we try to compare these different products. And one thing you will notice is that regardless of the region, they do not agree. There's a lot of disagreement between these different products based on the ways that they are derived. So we still have this major problem of uncertainty in fire emissions. And with that uncertainty, the modeling of phenomena that result from fires will continue to have problems. So just this, I'm showing it just to show a little bit of one aspect of what could be responsible for the uncertainty. For instance, this fire, the station fire that took place in Pasadena, I think several years ago. So Moody's, which is a sensor on two satellites, Terra and Alpha, the same instrument, two copies of the same instrument on two satellites, observing this fire. This one, at this time, the difference in time when this fire was observed, the same fire, was about 1.5 hours. So this one was looking at an area. So you see that the pixels are very square in shape. So it's able to see the fire as the way it is distributed spatially. But this one was looking very far at the edge of scan. So everything is clumped together. So that when you compare them, the measurements that they obtain, you see there's a very big difference. So this can contribute to the errors that we get when we use this to derive emissions. So these agencies, NASA and NOAA, came together and mounted this very big field campaign across the northern US. So we had two planes from NASA, 2 NOAA planes, and many ground crew, different groups. And we were stationed at Boise, Idaho, and then at Salina, Kansas, during the summer of 2019. And we flew these different regions. So stationed here, we flew the western fires. Over here, we flew the southeastern fires. So this was when we were here, like that picture that I showed in the beginning. So we'll see that, so one of the instruments aboard there, so I was the science leader of that instrument at that time, master, we were able to take this picture, which shows a very detailed, spatial of the fire, of different fires. And this is from there. These are the detections of fires from there. So you'll see that the spatial arrangement is very similar. So then from the high spatial resolution airborne sensor, we're able to not only retrieve the fire radiative power, but we're able to also classify the image into smoldering and flaming. Also, because the instrument, because of the high energy of the fires, the high flaming fires sometimes saturate the measurement because of the nature of the technology. So we also see some parts that are saturated. So anyway, the product that we measure from aircraft are being used to compare with what we get from satellites. So basically, this is the distribution of the measurements from different dates of the fraction of the fly that is smoldering or flaming or saturated. So that's what we plot here. This was developed by Sugar and her team at NASA, at NOAA and Estes. And so we also use the airborne data to compare with peers, which last week we mentioned, the battery power measurements. And we see that so these are the dates for the western fires. They agree mostly, but on the fires, the smaller fires, they do not quite agree. So we're still trying to learn why those discrepancies happen. And we also did the same comparisons with the airborne instrument and the Moody's. And we'll see the different agreements or disagreements. So basically, we're using the airborne measurements of the fires to validate the satellite measurements. And so we're also using the emissions we're deriving from the airborne measurements to derive emissions to plug into the WRF-CAN and simulate the smoke distribution, which you see there, which agrees with the satellite measurements. Anyway, a satellite observation. So in conclusion, in summary, smoke emission rate is directly related to the rate of biomass combustion, which is related to fire radiative power. That is effective in estimating smoke emission rates and other important quantities. we also say that current global emissions are still have a lot of uncertainty, but the agencies are coming together to try to organize campaigns to address this uncertainty. So that is all, and I would like to acknowledge support from NCASM. I'm part of NCASM, so the support from NOAA and the other sponsors and NASA and other colleagues. Thank you.